The human brain possesses a hardwired negativity bias. When exposed to a threat, the amygdala triggers a rapid autonomic response, shifting our cognitive resources away from background noise and directly toward the danger. This biological prioritization ensures we learn from hazardous situations. It results in flashbulb memories, recollections of shocking events that feel exceptionally vivid, detailed, and permanently etched into our minds. We see this mechanism operating at scale during public shock events, like the September 11th attacks. Decades later, survivors retain a high degree of subjective confidence regarding exactly where they were when they heard the news. However, subjective confidence is not the same as objective accuracy. Longitudinal studies show that the specific details of flashbulb memories still decay over time, even while the person remains entirely convinced their memory is flawless. In healthy populations, heightened emotion acts as an evolutionary highlighter. It ensures that significant events are prioritized over mundane ones, saving the most crucial data for future survival. This reliable model of memory enhancement breaks down when we examine the clinical presentation of patients suffering from severe post-traumatic stress disorder. Here we encounter a clinical paradox. Despite surviving the most extreme emotional threats imaginable, PTSD victims frequently present with fragmented recall, specific amnesias, and a marked inability to remember the central details of their own trauma. This creates a divide in the scientific literature. On one side, electrophysiological data suggests that high arousal enhances memory encoding. On the other, neuropsychological assessments of trauma victims document profound encoding failures. The central thesis of this video is that emotional memory encoding is not a linear process that scales endlessly with arousal. To understand the mechanics of PTSD, we must map the precise biological threshold where the brain's memory system overloads into catastrophic impairment. To locate this threshold, we first need to observe the enhancement system working optimally. In 2023, researchers Qasim and Jacobs at Columbia University used intracranial recordings in epilepsy patients to bypass the skull and monitor the amygdala hippocampal circuit directly. The experimental design was straightforward. Patients memorized lists of words carrying different emotional weights, comparing neutral words like chair against emotionally arousing words like knife or dog. The neural mapping revealed a specific biological mechanism. Whenever patients successfully encoded emotional words, researchers observed a surge of high-frequency activity, specifically between 30 and 128 Hz, synchronizing across the amygdala and the hippocampus. To prove this correlation was causal, the researchers initiated a second phase of the experiment. They applied targeted electrical stimulation to the hippocampus to deliberately disrupt this specific circuit. Knocking out the high-frequency activity yielded an immediate result. It selectively diminished the patient's ability to remember the emotionally arousing words while leaving their baseline memory intact. Undisturbed high-frequency activity across the amygdala and hippocampus is the mechanical prerequisite for encoding emotional significance into memory. The Columbia study tracked controlled memorization. To understand peritraumatic stress, the chaotic encoding that happens during an actual threat, we look to a 2014 study conducted by Chung and colleagues in Taiwan. The researchers sought to test the tunnel memory hypothesis. This is the assumption that extreme stress forces the brain to hyper-focus its encoding strictly on the central details of a threat, sacrificing any memory of the periphery. To simulate peritraumatic processing safely, the team recruited 45 domestic violence victims, divided into those with and without PTSD, alongside 31 healthy controls. All subjects watched an 8-minute film depicting domestic violence, while their physiological reactions were monitored, followed by an unexpected memory test. The post-film memory evaluation was strictly divided into two categories: questions testing the central plots involving the violence, and questions testing peripheral, neutral background details. This methodology serves as the ultimate stress test for the tunnel memory hypothesis. If extreme arousal narrows focus to the threat, the PTSD group should exhibit the highest scores for central details. Looking at the immediate and delayed recall for central details, we see the opposite of tunnel memory. The PTSD group scored significantly lower than the other groups. This wasn't generalized amnesia. Peripheral memory showed no statistical variance. The physiological data identifies the cause. The PTSD group experienced a massive spike in blood volume pulse. This cardiovascular spike indicates a state of severe physiological hyperarousal, occurring precisely during the central violence plots of the film. Severe hyperarousal does not create tunnel memory. Instead, extreme stress actively overrides the hippocampal circuit, disrupting high-frequency activity required to encode the central threat. If standard memory and neuropsychological functions remain intact in victims, we have to ask what cognitive metric actually predicts the severity of PTSD symptoms. This multiple regression analysis isolated the variables predicting the severity of re-experiencing, avoidance, and hyperarousal symptoms. Across all categories, the most powerful cognitive predictor is found right here: perseverative errors on the modified card sorting test. Perseverative errors measure a specific failure in executive function. It calculates an individual's inability to adaptively shift their cognitive strategies when the rules of a task change. It is a direct metric of mental inflexibility. The data points to a clear neurological protective factor. Possessing high mental flexibility, and thereby making fewer perseverative errors, serves as a primary defense against the maintenance of long-term PTSD symptoms. This graph maps the inverted U function of emotional memory. The intracranial data from Columbia University maps to the rising left slope. Moderate stress and emotional arousal climb the curve, triggering high-frequency activity and successfully enhancing memory encoding. The clinical data from Taiwan maps to the falling right slope. When peritraumatic stress pushes the nervous system past its operational apex, the circuit overloads, and hippocampal encoding plummets to a baseline. The brain does not possess a flawless threat recording system. It operates like a highly sensitive acoustic receiver, one that distorts and drops the signal when the volume of fear is turned up too high. For clinical application, this means practitioners must avoid conflating a patient's subjective confidence, the flashbulb feeling, with objective encoding accuracy. When trauma victims present with fragmented narratives or an inability to recall the central details of their assault, it cannot be misconstrued as malingering, psychological denial, or a generalized cognitive decline. These specific amnesias are a verifiable biological signature. They are the direct result of hippocampal overload caused by hyperarousal at the exact moment of the threat. Effective trauma therapy addresses PTSD as a systemic failure to encode the trauma into context. Without that bridge to the past, the brain remains permanently braced for an event it cannot fully process.